So today we're going to look at a confidence interval for a single population mean. You'll see some similarities between what we're doing today and what we talked about in our last section with confidence intervals for a proportion. And you'll also see some continuity with some of the ideas we'll be talking about later this week when we expand this to comparing two means to each other or two proportions to one another. So remember that this is all based off of the rule for sample means, which is derived from the central limit theorem. It's the big idea of statistics that allows us to perform these analyses. Remember that the rule for sample means says that if numerous samples or repetitions of the same size are taken, the frequency curve of means from various samples will be approximately bell-shaped, and the mean will be the same as the mean for the population. And the standard deviation will be given by this equation with population standard deviation divided by the square root of the sample size. So again, fits on this bell curve where that population mean goes at the center of the curve, and then we can count the standard deviations found with these, or found by this equation, going these step sizes to the left and to the right. Now, that step size, we have a better name for that. The name is standard error of the mean, or just standard error, and sometimes you'll see this represented as SEM. Calling it standard error allows us to only use that phrase when we're talking about this distribution of sample means, as opposed to if we called it like standard deviation step size, then there might be confusion that refers back to the standard deviation of the entire population. So again, this is an equation that you will see on your equation sheet that's linked at the top of the lesson page on Canvas. Standard error, or SEM, is population standard deviation divided by the square root of the sample size. Now the problem is we've seen that you're taking a sample to represent that entire population. So it doesn't really make much sense that we would have the population mean or the population standard deviation. So what we're going to be doing is replacing that population standard deviation right there with the sample's standard deviation. Remember, you're taking a sample of n number of individuals, and that sample is going to have its own standard deviation represented by lowercase s. Okay? The population as a whole, its standard deviation is represented by the sigma. Okay? So this standard error is that standard deviation step size for these distributions of means. So here's the example that we looked at in the previous lesson that was talking about these sample means. It's a weight loss example, and you're taking a sample from the population, and again, in the entire population, you know that the sample has a mean of 8 pounds and a standard deviation of 5 pounds. From our sample we're taking of 25 people, the mean weight loss of that sample, I'll go with a different color here, the mean weight loss of that sample was 8.32 pounds, and standard deviation for that sample was 4.74 pounds. So we can see the similarities between the population standard deviation and the sample standard deviation. The population standard deviation was 5 pounds. Our sample standard deviation of 4.74 pounds, that's pretty close. Close enough for our calculations. So the standard error calculation with the population standard deviation when it was 5 divided by square root of 25, gives us a standard deviation of 1. But if we substitute in our sample standard deviation of 4.74, again, it gets us a pretty close answer of 0.95. Now, In some cases, this is a better representation. If you have an extremely small sample size, you're probably going to want to use a t-test rather than the z-test that we're looking at right now, based off of that z-score chart that we've been using all year. We'll talk a little bit more about t-tests and when they're appropriate in the future. Once again, we do need to satisfy the conditions to be able to use these equations, that population that we're taking these measurements from is normal, and a random sample of any size is measured. Or, and this is very important here, if it is not a normal population that we're drawing from, that doesn't really matter, as long as that sample size is at least 30. But if you have a sample with a lot of variation and some extreme outliers, we always know the bigger the sample size, the better. So once those conditions are met, we're going to see a very similar procedure to what we did with proportions. To create a 95% confidence interval, again, we want to be within 2 standard deviations, or now that we're talking about means, within 2 standard errors of the center of that curve. We can create a 95% confidence interval by placing the sample mean at the center in place of the population mean, and we'll go 2 standard errors to the left and 2 standard errors to the right. So you see our equation, which is on your equation sheet, or I'll write it right here. We have x bar representing our sample mean plus or minus 2 of these standard errors, or you could replace it as x bar plus or minus 2 of these sample standard deviations divided by the square root of n. Oops. There we go. Down here on the bottom, we see, once again, like I mentioned previously, that it's important that if we have a small sample size, less than those 30 observations, that we're looking at using a t-test rather than a z-test, which means that we need to multiply this by a number that's bigger than 2. It has its own separate chart, and as I said, we'll look at that again in the future. So let's finish up by looking at an example here. At this weight loss clinic, there's a group that is trying to lose weight exclusively by diet alone, and there's another group that's trying to lose weight exclusively by exercise alone. And we're comparing their weight loss over the course of a year to men who diet but do not exercise, and vice versa. So let's look at the data for this diet-only group. Okay. Their sample mean, x bar, was 7.2 kilograms of weight loss. Sample standard deviation, S, was 3.7 kilograms, and the size of this sample was 42 individuals. So our standard error calculation, again, S divided by the square root of n. In this case, we see 3.7 divided by the square root of 42, our sample size, gets us a result of 0.571. That is our standard error, or that will be the step size that we're going to the left and to the right of that mean. So we can see our confidence interval for this population mean. We take our sample standard our sample mean, 7.2 right there, multiply by 2 of these 0.571s, and we get plus or minus 1.1 kilogram, which gives us a confidence interval in kilograms of 6.1 to 8.3 kilograms. We interpret this as we are 95% confident that the true population mean of weight loss, that true average weight loss, is going to be between 6.1 and 8.3 kilograms. Or you see that conversion into pounds between 13.4 and 18.3 pounds. Now, this was the diet-only group. If we wanted to look at that exercise group, here was their data. The sample mean was 4 kilograms, sample standard deviation, 3.9. Sample size, similar but not identical to the diet group. That's okay. We don't need to have exactly the same sample size. So their construction of their confidence interval, their weight loss of 4 kilograms, goes right there at the center of the curve. Let's kind of visualize this one. So we have 4 right at the center of the curve. Their standard error in this case works to be about 0.569. So multiply by 2 of those. So we're going 1 standard error to the left, 1 standard error to the right. We want to go 2 of those, which is why we multiplied by 2. So this confidence interval now is 2.9 kilograms to 5.1 kilograms, or again, going to pounds, 6.4 pounds to 11.2 pounds. So think about these two confidence intervals in relation to one another. Okay? Again, a confidence interval allows you to say that you're 95% confident that the true mean of the population falls between these two values. Okay? There is some built-in inaccuracy with that. 5% of the time you expect it to not fall on that interval, and you're okay with that. You recognize that in advance. To compare these two intervals to each other, again, for our diet group, we had an interval, let's go with the pound measurement here, 13.4 to 18.3. For the exercise group, that interval in pounds was 6.4 to 11.2 pounds. Now think about these two intervals. They do not overlap. If you're 95% sure that the true average weight loss due to diet alone was between 13 some pounds and 18 some pounds, and the exercise alone group, the average weight loss was between about 6.5 pounds and to 11 pounds, it appears like the diet group is a more effective method of weight loss based off of our samples. Okay, there's no overlap. If these two confidence intervals overlapped each other, then there's a possibility that they're essentially the same. But because these two groups are completely separate from one another, we have pretty convincing evidence that it's this diet group. If you're going to pick one method of weight loss, diet alone or exercise alone, it looks like we have convincing evidence that the diet alone method is a more effective method. Coming up in the subsequent lessons, we'll be looking at a more direct way of comparing these two. Okay? But for right now, we constructed 2 separate confidence intervals, and we were able to make some conclusions about relating them to one another.